Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Lecture 3 in Week 4, Microrefrigerator on a Chip. Today we are going to see how thermoelectric devices can be used to cool very small area on a chip, and what are the trade-offs involved in the design and optimization of the thermoelectrics. If you take a thermoelectric model, today most commercial models have thicknesses on the order of 1 or 2 millimeter. They have low cooling power density. One thing to do is that if you exactly make with the same material but tinier elements, the leg thickness scales inversely with the power density, cooling power density of the thermoelectric. So if we make the leg 10 times thinner, if everything is ideal, the cooling power density of the thermoelectric device increased by a factor of 10. So since mid-90s or so, there were companies like Micropelt that they try to make these tiny thermoelectric models where the leg thicknesses are so small that we can reach higher cooling power densities. Here is a graph that shows the power density of the thermoelectric versus, for example, cold side temperature or different leg thicknesses. Again, most coolers with 2 millimeter thickness have cooling power densities of less than 10 watt per centimeter square. And by going down to 20 micron or so, one could reach hundreds of watt per centimeter square. The best commercial thermoelectric models that you can buy, even the thinnest one, have something on the order of 100 watt per centimeter square. Why this, how this scaling happens, it comes from the energy balance of how the net cooling is a result of Peltier cooling minus Joule heating in the material and heat conduction. Joule heating in the material, half of it goes to the cold side, the other half goes to the hot side. In the lectures by Professor Lundström, you saw how this is derived. You can also calculate the COP of this device. You will have a homework where you will see how these equations could be manipulated and derive some of this cooling power density data that I showed you previously. About 12, 13 years ago, there have been some work on thin film thermoelectrics called Superlattices or quantum dot thermoelectrics. One of them was lead telluride selenide quantum dot by Ted Harman's group, with a claim ZT of 2, science paper in 2002, and then another one from RTI with a ZT of 2 to 2.4 in 2001. In both cases, the amount of cooling were about 30 to 40 degrees, so it was not more than state-of-the-art thermoelectrics, but the idea was that because of nanostructuring, you can get higher performances. In week 5, we go on of some of the physics of this and comparing experimental results with some of the modelings that Professor Lundström have described in week 2. But one aspect from a system point of view I want to emphasize is that to get this type of cooling performance, one does not need to get high ZTs. Actually, in the case of the Harman, later papers by Chris Menes showed that the actual ZT of this material is actually 1. The idea that you need to get very high ZTs to get localized cooling is not necessarily a requirement. Again, there is a very nice paper came out in 2009 that described thin film coolers, where a thermoelectric model is actually integrated inside a package. So you have a test chip, a substrate, a thermoelectric is integrated with a heat spreader, and here's a physical picture of that. Here are some of the measurement results from this paper in 2009 in Nature Nanotechnology. Basically, without no thermoelectric, the chip heats up to 125 degrees. there is a passive cooling of 7.6 degree because when you add some copper beneath the thermoelectric, it helps the heat path, so there is this much cooling. But then you add the thermoelectric thin film device with a current of about 3 to 4 amp. You can cool an additional 7.5 degree, and this is the total of 14 degrees. Again, the material here has claimed ZT of 2.2, but to get this type of cooling performance, if you put a ZT of 2.2 in the equations for thermoelectric, the cooling should be much more than this. So the main reason the authors mentioned that the cooling was limited is because of extra contact resistances, electrical and thermal. If we can avoid these contact resistances, thin film coolers could have an impact even with moderate ZT. Here is an example where a thin film cooler is directly integrated in silicon. This is kind of early work on silicon and silicon germanium carbon superlattices. Basically, by adding 1% carbon, you can make 10% germanium, silicon germanium layer lattice match to silicon. So as a result, you can grow all of it on top of silicon, and you end up with silicon. So you can have a full integration of silicon electronics. Underneath it is a 3-micron layer of superlattice. In lectures by Professor Landstrom, you saw that the superlattice barriers could affect electron transport by making the hot electrons move much more easily than the cold electrons. That could improve the power factor, and you can make a microrefrigerator devices out of it. Here is a side drawing, tell you a metal is deposited, there is an insulator underneath, metal electrodes send current, electrons here have a thermoelectric effect, and there could be also a thermionic effect because there could be selection between hot and cold electrons due to these potential barriers. Basically, near room temperature, this is a linear device, so linearized thermionic and thermoelectric can be treated the same way. This is like an effective medium with an adjusted Seebeck coefficient conductivity as well as an adjusted thermoconductivity. The question is how these devices, how much they cool. In the measurement section in week 3, we described that you can just put a microthermocouple with the same size as the device, about 50 micron diameter, and measure cooling. And this is the kind of cooling that has been obtained with currents on the order of 400-500 milliamp. You can get at 100 degrees Celsius ambient temperature, 7 degrees Celsius cooling. That means this area on the device is 7 degrees cooler than the surrounding around. And this is happening because we are sending current through this area. The cooling power densities are large, and we'll describe it a little bit. But here I want to show that here you have a device where you get the same 7 degree cooling, but with a material that its inherent ZT is not very large, and we will show later on what are the ZT numbers. Here are the results with different type of superlattices. In this case is silicon germanium with 25% germanium, where the layer thicknesses are 3 nanometer silicon, 12 nanometer silicon germanium, 200 periods. Another case where the layer thicknesses are different with 30% germanium and a bulk silicon. If here we have a bulk silicon, you can already get 1 degree cooling. That's the thermoelectric cooling of silicon. By making a superlattice, you can improve that by a factor of 4 to about 4 degrees at room temperatures. When you have silicon and silicon germanium without carbon, the lattice constant on the average is different from silicon, so you need a buffer layer, and this add extra resistances, electrical resistance, thermal resistances. So even with this non-ideality, still the top surface of this device could cool 4 degrees below ambient. How this cooling power density could be measured? So we take the same square coolers, on top of it we fabricate a thin film heater. The resistance of this thin film heater also changes with temperature, so it can be considered as a thermistor. So it's a perfect sensor and power source. When this is off, the device cools about 2.5 degrees. Before these heaters were fabricated on top of the coolers, the device cooled about 3 or 3.5 degrees. So this reduction is due to all the processing and additional heat leakage that reduces this cooling. But even with that, at 0 degree heat load, when you don't send the current to this heater, the cooling is 2.5 degrees. You have to apply up to about 600 watt per centimeter square to get the temperature on top of a device the same as surroundings. So the cooling power density is defined as to be 600 watt. So you can have 0 heat load on top and 2.5 degree cooling, 300 watt heat load on top with 1 degree cooling, or 1.2, and then 600 watt per centimeter square heat load and no cooling at all. So this is a way how the cooling power density is characterized. How the cooling power density scales with the device. Here is the maximum power density, the red curve, versus device area, 100 by 100 here, and maybe around 40 by 40 micron here. And here's the maximum cooling. You see in an optimum, devices with areas on the order of 4,000 micrometers square have the cooling of about 3.2 degrees, and when you go higher or lower, the cooling is reduced. In an ideal 1D thermoelectric device, the cooling is independent on the device area. The reason here is an area dependence is because of the parasitics. You have a heat leakage through the side of the device that scales with square root of the area. You have a heat cooling power that on top of a device that scales with area, and you have a thermal resistance due to heat spreading in the substrate that also scales with the square root of area. And because of these non-idealities, you get this type of optimum cooling. As you make device smaller and smaller, because you are spreading the heat from a localized location and spread it out, one could get cooling power density that go to 600 watt per centimeter square. So that tell you, even with a constant thickness of the device, you can reach high cooling power density in a three-dimensional geometry, and this is something that we will describe in future lectures. Other thing we can do with these coolers is that they can be inherently very fast. Here's the same cooler, but the electrodes, the metal, are designed in a coplanar way, a waveguide structure, basically a ground signal ground. Your signal is sent to the device, and then the current is sent back to the ground. Here it's shown by the arrows. Through the geometry and the size of these electrodes, this is optimized to be 50 ohm. Tapering maintains the 50 ohm, and then as a result, we can apply a very fast electrical pulses to top of a device. Here is thermal images obtained using the thermoreflectance technique that was introduced in week 3. In this case, you can see at times of couple of 100 nanoseconds, the cooler starts to be seen at the forward polarity where there should be cooling, a blue region, couple of degree cooling, and at the reverse you see heating. There is some localized heating at the necks. This is a fabrication error. Basically, we have a tiny device where current comes from the side, and because of the metal coverage on the side contacts of these electrodes here, you have an extra localized heating. By doing measurement both on forward and reverse polarity, we can look at what is the component which doesn't change with polarity and which is the component which changes with polarity of current. The component that doesn't depend on direction of current is Joule, and the one that changes with direction of current is Peltier. So you can nicely see that Peltier cooling happens at the metal semiconductor junction, while Joule heating happens in the electrodes and everywhere else. So this is a good way the characterization is done. An important point is for these devices to cool by this much, couple of degrees, what type of ZTs we need. Here is a little busy graph, but it tells you for specific materials from an article in 2006, what are the type of ZTs and coolings. A typical bismuth telluride alloy used in today's coolers cool about 74 degrees or so, and the Z times T is about 1. This is the Seebeck coefficient, electric conductivity, thermal conductivity, power factor is S squared times sigma, is on the order of 4, 10 to the minus 3 watt per Kelvin square meter. A silicon refrigerator can cool about 1 degree, even though the ZT is 0.007, very small ZT. The power factor of silicon is similar to bismuth telluride, is high. What is the problem is large thermoconductivity of silicon. Then here you can see in the two lines in the bottom, silicon germanium alloy, 3 micron thick device that has a maximum cooling of 4 degree Kelvin, and a superlattice device that has a maximum cooling of 4.2. So you can see basically lots of engineering of tiny layers, thermionic emission, reducing of the thermoconductivity, improve the cooling just only 5%, barely observable. When we measure the material property, we can measure thermoconductivity of material accurately using 3 omega, as you learn in Week 3. What you can see is that, surprisingly, the material that is alloy has a thermoconductivity that is lower than the thermoconductivity of a superlattice. So all the additional interfaces and so on did not reduce the thermoconductivity below the alloy limit. This is a case that sometimes breaking the alloy limit can happen, but not guaranteed, and in this case didn't happen. So the result is that the ZT of the bulk material is not that different from superlattice. Superlattice, again, is slightly better. So there is a significant improvement in power factor because, presumably because of these multiple barriers and energy filtering, but some of it is cancelled, or most of it is cancelled by the higher thermoconductivity. As a result, ZT is very low, on the order of 0.08. Even with these low ZTs, we are able to observe 4 degree Kelvin, 4 degrees Celsius cooling at room temperature, and 7 degrees Celsius cooling at 100 degrees Celsius. How much the material could improve if we could improve how much the cooling could improve if we could improve ZT. Here is the active silicon germanium layer figure of merit. The cooling in an ideal case, when non-idealities due to the context and so on are reduced, could be at most about 7 degrees. If you improve ZT from 0.1 or 0.008 or so to ZT of 0.5, the cooling goes up to 15 degrees Celsius, up to 30 degrees Celsius, depending if you increase Seebeck coefficient or decrease thermoconductivity. Again, this is another case where improvement of ZT by changing different parameters have different impacts. Why increasing Seebeck coefficient is better than decreasing thermoconductivity is because a thin film refrigerator wants to cool below ambient, and we're limited by the parasitics. As a result, increasing the Seebeck increases the power density, cooling power density, and has a more impact. Here is the curve for maximum cooling power density versus the same active silicon germanium ZT. We start again with 500 watt per centimeter square. If we go from a ZT of 0.1 to ZT of 0.5, the cooling power density have not changed a bit. Why? Because we have made the thermal resistance of the device more by making it lower thermoconductivity. While by increasing the Seebeck, we can reach about 2000 watt per centimeter square. Basically, the message is a 10 micron thick, 50 by 50 micron monolithic microrefrigerator with a ZT of 0.5 can cool a kilowatt per centimeter square hotspot by more than 15 degrees C. So in order to reach some of these high cooling power densities, we don't need to get high ZTs if we don't have to deal with lots of extra interfaces. Here is a curve that shows the potential for localized cooling. Whenever we have a microchannel, the amount of cooling this provides depends on how fast, how much fluid you push through the microchannel. If, for example, I have a 1 by 1 centimeter square chip and it's dissipating about 100 watt, the amount of pumping power needed to keep the chip temperature below 85 degrees Celsius, the maximum junction temperature, is about 0.1 watt, negligible comparing to the 100 watt chip. Now, if we make the chip instead of 100 watt to be 120 watt, the pumping power goes up, and pumping power goes up very quickly. This is a logarithmic scale. So the chip at about 140 watt needs hundreds of watt of cooling. That's one of the limitations. Once a microchannel is designed, you can dissipate low powers, but very quickly you're saturated. But now assume that I'm not dissipating the 140 watt uniformly in the chip. I have 100 watt uniform in the chip, and the blue line tell you I add a hot spot, which is only 500 by 500 micron square. It has only 1.5 watt. So instead of 100 watt is 101.5 watt. This is 600 watt per centimeter square localized. That localized heating create a hot spot, and if we want to bring that hot spot below the 85 degrees Celsius, we need to cool the whole chip. As a result, you see that the cooling power required to cool the non-uniform chip, the blue line with hot spot, significantly goes up. That's a potential where thermoelectrics could play a role. So here is a graph of how thermoelectrics are optimized. This is something that you will see in the homeworks, that by changing the thickness of the thermoelectric or changing the operating current, you can achieve the lowest temperature at the junction. Analytical equations are a little are complicated, but again, through the nanoHUB simulations, this is something you can play with and see how this optimization is done and obtain similar type of curves. Here is the end result, where the power on the chip is magnified. 100 watt is the uniform power, and here is the additional power that is in the hot spot. So we add 1 watt, 2.5 watt in the hot spot. The blue curve is the curve that I started with, and as you can see, if on the hot spot I have something on the order of 600 watt per centimeter square, only 1.5 watt extra, instead of 0.1 watt cooling power, I need more than 10-15 watt. That's a significant. I add a 10 micron thick superlattice cooler or a thin film cooler with ZT of 0.1, and now the cooling power is reduced from here to this much, 10 times more efficient. Sorry, ZT of 0.5. So you can see that with even moderate ZT, we have significant improvement in the cooling power. Why? Because the cooling power is applied selectively to the hot spot. Let me summarize that we looked at the thin film Peltier coolers and microrefrigerators on a chip based on silicon germanium. One could achieve coolings on the order of 7 degrees Celsius at 100 degree ambient temperature and cooling power density more than 500 watt per centimeter square. In applications for localized cooling, significant impact is possible even with the ZT of 0.5, but that needs full integration and minimizing interface resistances. Finally, selective cooling of hot spots can significantly reduce cooling power requirement for the whole chip when both of them are present. Later on this week, we will look at how this some of the geometry of the thermoelectric legs as well as grading of the material could affect the cooling performance for thermoelectrics. I look forward to see you in lecture 4.